The trouble with capital G. Henry Cavendish drilled a hole 3/4 of an inch deep into a 348-pound ball of lead and cemented a thermometer inside it. That ball was one of two, and the pair of them were the source of the gravity he was trying to measure. What they were pulling on was a 6-foot wooden rod with a small lead ball at each end, hanging from a thin wire inside a wooden case, free to swing. Cavendish had discovered that, when the big weights sat warmer than that case, the rod moved for reasons that had nothing to do with gravity. Warm lead heats the air beside it. Warm air rises, cool air falls on the other side, and the resulting circulation pushes on a delicately suspended rod in a way the instrument cannot tell from a nearby mass. He tested it deliberately. Lamps under the weights heated them until the case's temperature had risen 1.5 degrees Fahrenheit over half an hour, and the rod then swung roughly 5 times as far aside as it should have. Then he packed the weights in ice. With the lead about 8 degrees colder than the air, the instrument reported the pull as weaker instead. This was 1797 and 1798, in an outbuilding in the garden of his house on Clapham Common. Cavendish was measuring the mean density of the Earth, which is the same problem as measuring the strength of gravity. The Earth's pull on a falling object is easy to observe, so if you can find out how hard a known lump of lead pulls, you can work out how much Earth there must be to pull the way it does. His answer was that the planet is about 5.5 times as dense as water. Converted into the modern constant, which runs inversely to density, that comes out roughly 1% high. That modern quantity is the gravitational constant, the number that fixes how strongly any two masses anywhere pull on each other. Newton's law of gravitation is written with it as a capital letter G, and physicists say big G to keep it apart from little g, the acceleration of a dropped stone. Its value is about 6.6743 times 10 to the minus 11 in metric units. Everything in dispute is in the last digit or two of that. 228 years after Cavendish, big G is known to about 22 parts per million. Measure a mile that well, and you would be right to within 1.5 inches. The fine structure constant, which sets the strength of electromagnetism, is known to about 2 parts in 10 billion. Against that, the gravitational constant is the worst measured of the fundamental constants. Nor is 22 parts per million a settled figure. The international committee responsible reaches it only by widening what every contributing experiment claims for itself. Gravity being weak is half the problem. 2 1-kilogram copper spheres touching each other pull on one another, with about 2 billionths of what either of them weighs. Convection, magnetism, seismic vibration, electrostatic charge on anything that moves, and the slow settling of the building all operate at that scale. The other half does more damage. Almost every other fundamental constant sits inside a web. The fine structure constant can be reached by several completely unrelated kinds of experiment, and all of those roads have to arrive at the same place. When one of them does not, the disagreement is visible and it points somewhere. Nothing like that exists for gravity. CODATA, the committee that publishes the internationally recommended values of the constants, states it plainly. Values of the gravitational constant are unrelated to any other data and are handled in a separate calculation of their own. No theory predicts what it ought to be. The only way to check a measurement of big G is against another measurement of big G. A century before Cavendish sealed his shed, Newton had already decided that weighing the Earth against a mountain was impossible. In the treatise printed alongside the Principia, he wrote that whole mountains would not be sufficient to produce any sensible effect, that a hemispherical mountain 3 miles high and 6 broad would not draw a pendulum 2 minutes of arc out of true, and that such forces were perceptible only in bodies the size of planets. 2 minutes of arc is 1/30th of a degree, or 120 seconds of arc, and it was well within reach of the instruments of his own century. A real mountain gives about 1/10 of that. Pierre Bouguer, a French mathematician, tried it first, on Chimborazo in what is now Ecuador, in December of 1738. He was there with an expedition measuring the shape of the Earth, and set up 2 stations to see whether the mountain's bulk would tug a plumb line sideways. It did by around 8 seconds of arc. That is far less than it should have been if the mountain were made of the same stuff as the planet under it. So Bouguer was driven to conclude that the Andes were less than a quarter as dense as the Earth's interior, a density no rock has. His notes from the 2nd station record a wind that filled the observer's eyes with sand, and was continually on the point of carrying away the tent. He had 10 stars, a 2.5-foot quadrant, no proper survey of the mountain's shape, and little confidence in the result. He also suggested that somebody repeat the work somewhere more comfortable. 34 years later, Neville Maskelyne, the astronomer royal, put exactly that to the Royal Society, arguing that it would do honor to the nation where it was made. A committee funded it out of money left over from the transit of Venus expedition, and sent the surveyor Charles Mason to find a suitable hill. Mason settled on Schiehallion, a mountain in Perthshire that is isolated from its neighbors, runs in a nearly symmetrical ridge east to west, and is steep enough on both flanks that an observatory could be planted close to its center of mass. The job of running the experiment then passed to Maskelyne himself. Maskelyne spent 4 months on it in 1774, making 337 observations of stars from camps on the north and south sides. The stars said his 2 camps were about 11.5 seconds of arc further apart in latitude than the surveyor's chains said they were. That gap is the mountain, tugging both plumb lines toward itself and tilting the instruments that were leveled against them. Turning it into a density meant knowing the exact volume and shape of the hill. That fell to the mathematician Charles Hutton. He divided Schiehallion and its surroundings into vertical prisms, like the cells in a piece of honeycomb, and summed the pull of each one. Where the survey had no measured height, he sketched faint lines joining points of equal altitude across his map and interpolated between them, which gives him some claim to the first contour lines ever drawn on land. 2 years and about 100 pages later, he announced a mean density for the Earth of around 4.5 times water, 18% low. He concluded, correctly, that the planet must have a dense metallic core. The survey ended with a party at which the Northern Observatory burned down. It took with it a fiddle belonging to one of the surveyors. Maskelyne, who had been listening to the man play for 4 months, replaced it with a violin that still exists and is known as the Yellow London Lady. John Smallwood redid Hutton's calculation in 2007 with a digital elevation model reaching out 120 kilometers and the modern geological map of the hill. Maskelyne's observations, reanalyzed with modern geology, give a mean Earth density within about 0.5% of the true value. That 18% error was never in the astronomy. It was in what Hutton had to assume about the density of the mountain. Cavendish improved on all of this because he built his own mountain, out of lead, and knew exactly what it was. He did not design the apparatus. John Mitchell, a Yorkshire rector and former professor of geology at Cambridge, had devised a torsion balance for the purpose some time before 1783. A rod hung from a wire so fine that a minuscule sideways force will twist it a measurable amount. He finished building it shortly before he died in 1793 and never ran it. It passed to the Cambridge professor Francis John Hyde Wollaston, who lacked the facilities for it and handed it on to Cavendish, who rebuilt most of it and kept Mitchell's plan. Where Mitchell had specified 8-inch attracting weights, Cavendish used 12-inch ones weighing 348 pounds each, which roughly doubled the force he had to detect. Both large weights hung from a crossbar that could be swung around by a cord running over a pulley through the wall. Cavendish was chasing a force equal to the weight of about 0.02 of a milligram. He sealed the room and observed the rod from outside through 2 telescopes set in the walls, reading ivory scales divided to 1/20 of an inch and lit by lamps aimed at them from outside. He admitted no other light and never went in during a run. 17 experiments came out of it, 29 separate results, spread over the summer of 1797 and the spring of 1798. His published mean was 5.48 times water, and it was wrong, because he had added one of his own results as though it began with a 5 instead of a 4. Francis Baily, an astronomer, reported the slip in a long memoir of 1843 and corrected the mean downward by about 0.5%. It had hidden well. Cavendish ran the experiment on 2 suspension wires, and the 23 results from the second wire genuinely do average 5.48, which made his 2 runs appear to agree exactly. Baily ran his own version in a room of his London house, chimney stopped, window papered over. He varied everything he could think of: balls of lead, glass, ivory, and platinum, suspensions of silk and brass and iron, and on some runs a bare rod with no balls at all. His first 1,300 observations, taken over 18 months, came out so discordant that he threw all of them away. James David Forbes suggested the trouble was radiant heat, and that gilding the apparatus would make its surfaces reflect rather than absorb. Baily lined the box with foil, wrapped it in flannel, and put it inside an outer case gilded on the outside. More than 2,000 determinations, across 1,841 and 1,842, gave him an answer nearly 3% too high, far outside his own stated error. John Henry Poynting, working in a Birmingham basement, thought he had a complete determination in 1888, and then found that the entire floor of his laboratory tilted by about 1/3 of a second of arc when he moved his mass, and that the tilt was worsening as a gas engine recently installed next door shook the building. Charles Vernon Boys made the century's best measurement by making the apparatus smaller. Boys proved that if the swing period is held constant, a torsion balance's sensitivity does not depend on its linear dimensions at all. Shrink the whole instrument, and the inertia of the rod, the restoring force of the wire and the gravitational pull all fall together, so the deflection stays the same. The advantage of the small version is that a small thing is far easier to hold at one temperature, and temperature differences are what drive the convection Cavendish had to chase out of his own apparatus. What had made miniaturization impossible was the suspension, because no metal wire fine enough to give a long swing could carry the beam. Boys solved that by inventing quartz fibres, drawn by attaching a blob of molten quartz to an arrow and firing it from a crossbow. His final apparatus had a 1-inch beam and gold balls the size of peppercorns, and it lived in the cellars of the Clarendon Laboratory in Oxford after vibration drove it out of South Kensington. Even in Oxford, weeknights were ruined by railway shunting a mile away and by street traffic 1/4 of a mile off. In the paper itself, he explained that he was stopping because the strain was too severe. 3 years without holidays, sitting up through Saturday and Sunday nights at the end of a week's work. His answer stood as the best available well into the 20th century. There are 2 classical ways to run a torsion balance. One lets the rod deflect and measures how far it goes. The other, dating to 1852, measures how fast the rod swings, with the masses in 2 different positions, and takes the difference between the 2 rates. Kazuaki Kuroda showed in 1995 that the second one had been biased high for 140 years. That method assumes that a fiber's stiffness is a fixed property of the fiber. Real materials have internal friction, so a torsion fiber's stiffness depends slightly on the rate at which it is twisted. 2 configurations swinging at 2 different rates see 2 different stiffnesses, and the difference does not cancel. Kuroda showed the bias runs upward, and that it shrinks as the fiber's quality factor rises, quality factor being the standard measure of how little energy a swinging thing loses per cycle. For a tungsten fiber of ordinary quality, it comes to about 160 parts per million. 2 years later, Charles Baily and Gabriel Luther tested it directly, running the same experiment with two tungsten fibers of deliberately different quality. Kuroda's theory said the worse fiber should read 315 parts per million higher than the better one. Measured, the gap came out at 345 parts per million. The classic time of swing measurements, including the ones underpinning the recommended value at the time, all had to come down. Sitting on the table alongside, all this was a result nobody could place. A group at the German National Metrology Institute had published, in 1995, a determination that used a beam balance floating on a bath of liquid mercury rather than hanging from a fiber. Their answer was 6.715, against a recommended value of 6.673, with a quoted uncertainty of 83 parts per million. That gap is more than 40 standard deviations, which means the two cannot both be right. With that number unexplained and Kuroda's correction unsettling everything older, CODATA in 1998 raised the published uncertainty of the gravitational constant from 128 parts per million to 1,500. That mercury result was withdrawn in 2004, after another group's modeling identified the cause, an electrical calibration term left out of the analysis. Recovery has taken a quarter of a century and is not finished. In 2000, Jens Gundlach and Stephen Merkovitz at the University of Washington sidestepped the fiber problem entirely by mounting the torsion balance on a turntable and continuously turning the turntable to cancel any twist. With no twist, fiber stiffness cannot bias anything. Nobody beat their 14 parts per million for 18 years. Terry Quinn's group at the International Bureau of Weights and Measures near Paris built a torsion balance hung from a wide, thin metal strip instead of a round fiber, and ran it two ways, once letting the rod deflect, and once applying an electrostatic force to hold the rod still and measuring the voltage needed. Holding it still is called servo mode, and because the strip never twists, its stiffness drops out of the answer. The Paris determination came out about 190 parts per million above the world average. In Colorado, a pair of hanging pendulums and a laser interferometer gave an answer roughly 290 parts per million below that same world average. That group later found two errors in their own analysis. One of them, a laser aimed about a millimeter off the line, joining the centers of the masses. Their correction, published in 2019, raised their value and nearly doubled their uncertainty. Two measurements made in one laboratory in Wuhan and published in 2018 are the most precise ever taken. They disagree with each other by 45 parts per million. The group at Huazhong University of Science and Technology, whose quoted uncertainties were about 11.5 parts per million, ran the classical time of swing method alongside the turntable method Gundlach and Merkovitz had built. Their own summary of the field was that a discrepancy of up to 500 parts per million in recent determinations suggests there may be undiscovered systematic errors. 16 measurements now feed the recommended value, and getting them to agree statistically requires multiplying every one of their error bars by 3.9. In 2015, a group led by John Anderson pointed out that the published values, plotted against the dates they were taken, look periodic, on a 5.9-year cycle, matching a known wobble of the same period in the length of the day. Two independent statistical re-examinations then found that a model with an extra unknown noise term fits the data far better than any wave. NIST, the American National Institute of Standards and Technology, held a workshop on the gravitational constant in Maryland in 2014. Its own write-up of the meeting was headed Trouble with a capital G. Terry Quinn stood up at that meeting and proposed shipping the Paris torsion balance, the one that had produced the high outlier, across the Atlantic so a different team could run the same instrument. A team led by Stefan Schlaminger ran the balance with copper source masses, and then with sapphire ones, in both modes. Their analysis was blind. NIST mass group multiplied the source mass values by a secret factor differing from 1 by up to a part in 1,000, and sealed the real number in an envelope, to be opened only once the analysis was locked. It was opened in front of an audience at a conference in Colorado in July of 2024. The results were published in April of 2026. Their answer sat 60 parts per million below the current recommended value, and carried an uncertainty of 57 parts per million of its own. 60 against 57 is close enough to call agreement and far too loose to call confirmation, and the paper's conclusion is that the result corroborates neither the earlier value nor the recommendation. The same instrument, in Paris, had produced a value 250 parts per million higher. They went looking for the reason, checking the shapes of the masses, the gas pressure in the vacuum, the optics, the temperature gradients. Schlamminger's summary was that they could not identify a single smoking gun, and that the cause is probably a multitude of things. One thing did recur, though not at the same size. In Paris and in Maryland alike, servo mode reads lower than letting the rod deflect. In Paris, that gap was about 100 parts per million. At NIST, it was about 60 parts per million with the copper masses and 150 with the sapphire ones. The paper calls it a reproducible but unmodeled physical bias that nobody has yet been able to explain. The practical consequences are small and specific. An orbit gives the product of the gravitational constant and a mass, never either one alone, and that product is known for the Earth to about 2 parts in a billion, and for the Sun to better than 1 part in 10 billion. Dividing the constant out to get an actual mass in kilograms injects all of its uncertainty at once. So in 2015, the International Astronomical Union defined nominal solar and terrestrial mass parameters as exact conversion constants, so that published stellar masses would stop twitching every time Codator revised the constant. The NIST paper treats new physics as the remote explanation and subtle instrumental systematics as the plausible one. From that it draws a conclusion about strategy. Adding more measurements does very little, because the earlier inconsistent results still dominate the average, and more data alone cannot resolve the tension among what already exists. The better move is to go back and re-examine the outliers.